Hello, I'm Duncan. Welcome to my energy efficient house.
Thank you, Duncan, for the opportunity to come to your house and to discuss some of the aspects that make it so special. Tell me what your philosophy was when you designed the house.
I've been a builder since 2000 when I started my business, and the main impetus right from the beginning was working on large subdivisions was just the bad design and very high wastage in these cookie cutter approaches. It was very unsatisfying to work on, and so I decided that when I started my own building business I'd specialise in sustainable building principles. Sustainable building, that word means a lot of different things to different people. Certainly not an absolute, but from my perspective it was how to build a comfortable home that minimises the lifestyle costs.
This is certainly a comfortable home. What did you build the house with?
The structure is made from Hempcrete on a concrete slab, insulated concrete slab. The house structure has been built out of a Hempcrete shell, if you like, which surrounds the timber frame, so it's not load bearing, on a concrete slab, which is insulated, based on passive house design, so the building is very well sealed, and Hempcrete helps that by being a continuous pour material. With an air recovery system that changes the air over once every 3 hours in the building to keep fresh air coming in, but getting exhausting stale air.
Why is Hempcrete so special?
I weighed up my options looking at what we actually wanted from a material, and it had to be very versatile in its forming, in its ability to take up different shapes. Straw bale I looked at because of its high insulation, but it didn't give me that option of being able to form it nearly as versatile as Hempcrete. Hempcrete, it's basically carbon neutral. So from two directions, the plant itself, the growing of the plant, and then which is then put into the walls is permanent storage of carbon. Then the lime binder, that calcifies over 100 years, so that the lime binder actually becomes more and more like a concrete rigidity over that time as it calcifies, and that's drawing carbon out of the atmosphere while it's doing that. In terms of carbon miles, we could source hemp from New South Wales, which was better than any other material. The binder, unfortunately, has to be imported, the lime binder. The insulating characteristics of hemp are extremely good. I've been conservative in classifying as R3 for a 300 thick wall, but I've seen English statistics that suggest that that's higher, up in the 4.5s, the R4, 4.5.
But the air tightness is the important aspect.
The air tightness is very important. Vermin, there's no cavity, so vermin can't nest in the walls or create any sort of destruction. It's termite proof. Termites hate it because of the alkalinity. So as long as the termites don't get to your timber frame, then it's very effective.
What have you done with windows?
The windows are triple-glazed timber windows, and we've put a low E coating on the outside because we're looking for summer performance. Being a farm, it was very important to have that summer performance for this climate, but also because putting virtually a broad-brimmed hat on the house with a deep veranda enhances summer performance but reduces winter performance in that trade-off. But it protects the windows and the external walls of the building. And in terms of life cycle cost, that's extremely important to me because it's designed with a view of lasting indefinitely, whatever that means. So protecting the building from the elements is extremely important. So we sacrifice passive solar so that the sun from the north in the winter, we sacrificed that for the long-term resilience of the building by having the deeper verandas. And on a farm, it's important, particularly for us, to have working space outside the building structure, which the veranda gives us.
The house feels very warm and comfortable today. So how are you warming the house?
The house is warmed by a wood heater.
Mm-hmm.
It's based on high thermal mass, with a very large surface area of that thermal mass exposed to the heat of the fireplace. So the fireplace absorbs I think it's 90% of the heat before it goes up the flue. A standard chimney might be, an open fireplace might be 10% efficiency. A combustion system can get up to 85-90% efficiency in burn,
Mm-hmm.
but it's a blast of heat for a short period of time, whereas the thermal mass of the chimney absorbs that heat and then radiates it into the room over a 24-hour period. So we will burn 20 kilos of wood over a 4-hour period in the evening, and that will then maintain the temperature in the house in the living areas at 21 degrees and in the bedrooms about 15-16 degrees. And it's also ducted. The air for the chimney is ducted directly from outside, so it's not drawing air from inside the building. It keeps the building sealed and reduces any carbon build-up, carbon monoxide, etc. in the building as well, or eliminates it. So the actual burning chamber of the chimney and the process of it, air intake and exhaust, is completely sealed off from the internal environment.
So how do you keep the air fresh in the house?
We use a heat recovery and ventilation system, which runs on a 30-watt fan, so very low consumption. It runs 24 hours a day. It draws air in from outside, from an air inlet 40 metres from the house, goes underground, comes up into the unit, and the heat exchanger in that unit draws the external air through the unit, but transfers the internal air temperature to that incoming air from the air being exhausted at about a 90%.
So where are you drawing the air into that system from?
It's drawn down 40 metres to the north of the house. It goes down 1.5 metres underground, where the average ground temperature is around 13 degrees. And so it preconditions the air so that it makes the transfer in the actual system much more efficient, because the air is already closer, that much closer to what the exhaust air temperature is likely to be. So in winter day like today, when it was about 9 degrees outside, the underground pipe will warm that to about 13 degrees, so it gains 4 degrees before it gets changed over, before the heat exchanger does the rest of the changeover. But other times, like summer, it might be 40 degrees outside, but it's probably 13, 14, 15 degrees down at 1.5 metres underground. So the air will come through and probably be about 16 degrees when it comes into the unit. So that's a huge difference, a huge drop in temperature before you have to start transferring the 21 degrees to that temperature to bring them into equilibrium.
So you're running a fully electric house?
No, we have gas cooktop, and part of that, we have a photovoltaic system on the sheds which runs the house. We couldn't have it on the house because our tree coverage in the garden would shade them too much, and also we have limitations on the cabling as well from the pre-existing house here. And I'm bringing that up because part of that is spreading the risk, because our electricity supply, as you'll know, it can be unreliable at times. And so the reason I put in the photovoltaic was because we're running a farm too, and also a rural property means that everything relies on pumps and energy, whereas in city environments and town environments it's not. So we need to have reliable energy. So we put the photovoltaic on for that. But part of the risk management too is to have gas on hand for cooking, because we have had times when 3 days in the winter where it's a heavy fog or heavy cloud, and we need to boost the hot water service with electricity, it runs the system down very quickly. And we have had situations where we've had neither grid nor PV, and we can still cook.
You spoke about thermal mass earlier. Tell me a little bit how you've got the concrete slab floor. How else have you got? And you've got the chimney. How else have you got thermal mass built up in the house?
Originally we were going to just have hempcrete external walls, but it's after doing the sums, worked out that if we added sand to the hempcrete, we could use the hempcrete for internal walls. By adding sand to the mix, it meant that the internal walls could become a real benefit by being a thermal bank, so absorber of heat, just as the slab does. So increase the efficiency and the stability of the temperature in the house significantly.
I notice you don't have any split systems to cool the house.
No air conditioning required.
And that's worked well for you?
It has.
Because of the thermal mass works to make that work.
It does. Because like any typical house, the house is sealed, but there's no problem with opening windows.
Right.
You know, it just means that you're using that system instead of relying on a heat recovery system. It doesn't confuse or throw anything out or whatever. So on a summer's night, and if the air temperature drops outside lower than what it is inside, we will open the windows and get cross flows right through the house, and that will then take that excess heat out of the internal mass and extract it from the building.
So you purge the heat from the house?
Yeah. So if we have night after night of hot weather, we'll have an issue, but it generally won't go above about 24 degrees inside, because you've still got the heat recovery system drawing air through the pipe under the ground, bringing it down. So extracting a certain amount, but if you've got day after day of heat in summer and at night, it does have its limitations.
Thank you very much for your time.
Pleasure. Thank you.